In today's lecture, we'll start talking about a very important concept in programming, and that's the notion of arrays. Arrays are very useful for storing and manipulating large volumes of data. So as an example to motivate the use of arrays, let's consider the following two problems. The first problem is very simple. You are required to read 10 integers and find their average. We know how we can do that. We can write a simple loop, and in each iteration of the loop we read an integer and add it to the sum, and at the end of the loop we just simply divide the sum by the number of integers, and that gives us the average. The important point is that in this algorithm we do not need to store all the integers that we have read at the same time. What we need to remember or store is only the most recently read integer. Now contrast that with this second problem, where we are supposed to again read 10 integers, find the average, but now find out how many integers in the input were less than the average. Now if you were to solve this problem, we'll have to first find the average as before, but then we'll have to look at each number again and compare it with the average to find out whether it is less than or equal to or more than the average, and count the number of integers which are less than the average. This means that we cannot forget an integer soon after reading it. We must remember this integer, we must store its value in some variable so that later it can be retrieved. Now without the use of arrays, we could solve this problem by having maybe 10 integer variables, but then the problem will be that we'll have difficulty in writing the loop because the variable name will change for every iteration of the loop. The arrays allow us to solve this problem very elegantly, as we'll see soon. So as we have seen, an array is essentially a mechanism that allows us to store and systematically manipulate large number of values. An array is what is known as a structured type. In contrast, so as I mentioned, arrays are a mechanism that allow us to store and systematically manipulate large number of values. So in contrast to the simple types that we have seen so far, an array is a structured type. That is, an array is composed of values of simpler types, and this is how we declare an array. We'll soon see number of examples. Here is the first, what we have to write is the base type. The base type is the type of the individual elements of the array. An array is composed of a large number of individual elements which are of some type. They have to be all of the same type. So this base type is the type of the elements of the array, and then the variable name is the actual name of the variable that represents the array, and then within the square brackets we have to mention how many elements of this base type will the array have. So the base type can be any type that we have seen so far. The number of elements must be a non-negative integer constant. That is, the compiler at compile time must be able to figure out how many elements are there in the array, and therefore how much space in memory is to be allocated for that array. So let's see some examples of array declarations. So here is the simplest example. Int here is the base type. The name of the array or the variable name is numbers, and 50 is the size of the array, and this declaration essentially says that numbers is an array which will be comprising of 50 integers. Here is another array. So this time the array name is P, the number of elements is 20, and the type of each element is char. This shows that the base type can really be any type. In this next example, the base type is short, and instead of giving the size as a literal constant, we have used a symbolic constant which we define using this hash define, which should be familiar to you already from earlier examples. So this size of the array need not be a literal constant, but it has to be a constant value whose value can be determined by the compiler at compile time. Here is the next example. In this case, we have declared the size of the array to be capital N, where N is declared to be a constant in a different way. This style of declaring constants is also something that we have already seen, and the base type in this example is unsigned long. Here is an example in which the array declaration is invalid. That is, if we have such an array declaration in the program, then the compiler will give an error, and the reason is that the size of the array has been declared to be n, which is the name of a variable here. So this is not allowed because, as I said, the size of the array has to be a constant which is known at compile time. Okay, let's now talk about how we can access and manipulate the individual array elements. So if an array we have declared to have n elements, then these array elements, these n array elements can be accessed as a0, a1, a2 up to an minus 1. So essentially the array element is accessed by giving the name of the array, a for example, and then within the square brackets the number or the index of the array element that we wish to access. And if an array has n elements, then the index will range from 0 to n minus 1. So we can have expressions like this which denote array elements, and such expressions can be used both on the left and the right sides of an assignment. Here are some examples. So this assignment statement is assigning the value x minus y to the fifth array element. Remember that the array elements start from the 0th element and go up to the n minus 1th element, where n is the size of the array. In this second example, the array element aj plus 2 occurs on the right side of the assignment, and the other thing you should notice about this particular assignment is that the array element index which is being used here is not a constant. It is j plus 2, where j could be any variable whose value will be known only at runtime. So only while declaring the array the size has to be declared as a constant, but while accessing individual elements of the array, the indices used can be arbitrary expressions which result in an integer. Here is one more example showing how an array element can be read from the input. We are using the familiar scanf library function for doing that, and the way we are doing that is very similar to the way we read a normal integer variable. When we read an integer variable, we say scanf %d %x. If we want to read in the value of the ith array element, then all we have to say is, instead of %x, %ai. Now it's very important in programs to be careful about the indices that we are using for the array elements. As I have mentioned earlier, if the array has been declared to have n elements, then the array indices range from 0 to n minus 1, and it's very important to ensure that the array element that we are accessing has an index between 0 and n minus 1. So for example, suppose we have declared an array to have 100 elements. What will happen if the array index used in a particular expression is less than 0 or more than 99? The answer is that in this case the results of the program execution will be unpredictable. We will not be able to say what will really happen. This is an error because we are not allowed to use array indices less than 0 or more than 99 in this case where the array has 100 elements. But the C compiler does not check these kinds of errors, and so what will happen at runtime is some unpredictable and unexpected behavior. Therefore, it's the programmer's responsibility to ensure that the array bounds are not violated. And violation of array bounds actually is a very common problem in many programs. Many programmers make the mistake of accessing array elements which do not exist, and such errors do not necessarily always result in the program crash. They can have other unexpected effects, and so therefore and these errors are very hard to track down. Therefore it's we need to be very careful while dealing with arrays that the expression that we are using for an array index is within the bounds for the array. Okay, so now here is our first simple example program using an array, and this is the problem that I mentioned earlier while motivating the use of arrays. You have to read 10 integers and find the number of integers that are smaller than the average. So we start with the declaration of the variables. The variable sum is the one that we'll use to store the sum of all the integers that we read. Num10 is the array which we'll use to store all the integers that we have read. Recall that once we have computed the average by summing up all the integers and dividing by the number of integers, we'll need to once again look at each integer that we read and compare it with the average to find out whether it is less than the average or not. The variable count will be used to count the number of elements which finally turn out to be less than the average, and the variable avg, or standing for average, will contain the average, and this can in general not be an integer, and so therefore we have used the float type to store the average. So this loop is as before. So we are trying to read 10 integers and find their sum. So this for loop runs 10 times for values of I from 0 to 9, and each iteration of the loop we read the ith element of the array and also add it to the sum. After that, once we have found out the sum, the average is nothing but the sum divided by 10, but we have to be a little careful here, because remember that the sum, the variable sum is of type int, and the literal constant 10 is also of type int, which means that if we just divide sum by 10, we'll do an integer division, which will mean that the fractional part of the result will be dropped, and the final value that we'll get will always be an integer. So therefore, to avoid that, we are first typecasting sum into a float, so that one of the operands of the division is now a float, and so automatically the other operand, which is 10, will also be typecast to a float by the compiler before the division, and the answer will retain both the integer and the fractional part of the result of the division. And finally, having found out the average, this loop is being used to find out the number of elements in the array which are less than the average. Note that we have again used the comma operator from the previous lecture to make two initializations in the for loop. We are initializing count to 0. Remember, count is the number of elements that are found to be less than the average, and I is also assigned to 0. This is the loop variable. This will run from 0 to 9. When I becomes equal to 10, the loop will terminate. So within each iteration of the loop, if the ith element that we read, or the ith integer that we read, is less than the average, we add 1 to the count. And note again that this entire statement is a single if statement, and therefore we don't need braces around it to make it the body of the for loop. And finally, this statement is outside the for loop. This will be executed once the for loop finishes, and this simply prints the value of the variable count, which is nothing but the number of integers that have been found to be less than the average. Next, we come to array initialization. As you know, when we declare variables, we can initialize them with a value at the same time. The same thing can be done with arrays as well. And array initialization is quite simple. All you have to do is that the element values of the array in the order of their indices have to be placed in braces, and they have to be separated by commas. So we'll see an example of the use of such kind of an array initialization. Suppose we are writing a program that finds the day of the week for a given date. So what we need to do probably is to store the number of days in each month in an array, and since these are constant values, we can initialize this array right at the time of declaration. So our program might look something like this. So we define symbolic constants for the various months from January to December. January is defined as 1 and December is defined as 12. The number of months is of course 12, and then we have this array month days, which stores the number of days for each month. Now we want to refer to January, month January with the index 1 in this array. Let us say we could of course also have used 0 for January and 11 for December and so on, but that might have become a little unintuitive. So but recall that when we declare an array to be of size n, then its indices range from 0 to n minus 1 and not from 1 to n. And since we need indices from 1 to 12 in the array, we'll need to make the array size 1 larger than the number of months, and so therefore the array size is number of months plus 1, which is of course 13. So that means that the array has elements at indices 0 to 12. the element at the index 0 will not be used, so we are assigning it a value 0, and the rest are the number of days in the various months from January to December, ignoring of course leap years. So as you can see, these array values, initial values of the array elements, have been placed in the order of the array indices, and they have been separated by commas, and they have been enclosed in these curly braces. So this is how we can initialize an array. Okay, next we come to higher level arrays, or 2-dimension or higher dimension arrays. These are very useful for manipulating structures like matrices and so on and so forth. So as an example, this is a very common engineering problem. Suppose you want to solve a set of n simultaneous linear equations in n variables, then we need to store the coefficients occurring in the n equations. So these can be easily stored. In mathematics, we represent them as an n cross n matrix. So in C, they can be easily stored as a 2-dimension matrix or a 2-dimensional array, and the solution vector can be stored as a 1-dimension array as usual. So let's see how we can declare and use 2-dimensional array. So conceptually, a 2-dimensional array is just like a matrix or a table with a certain number of rows and a certain number of columns, and one value at each cell of the table or the matrix. So when we declare an array of 2 dimensions, or indeed for higher dimensions, again what we need to do is to specify the base type of the array elements, the name of the array, in this case matrix. The base type in this example is int, and then we have to give the number of rows and the number of columns, both in square brackets, one after the other. The first is the number of rows, and the second one is the number of columns. Again, the number of rows and number of columns again have to be constants whose values can be determined at compile time. So in this example, the number of rows in this matrix is m, and the number of columns in this matrix is n. And while accessing array elements of a 2D array, we have to specify the indices for both the dimensions. So just like a matrix element is referred to as Aij, if A is declared as a 2-dimensional array, then we have to access its array elements as Aij in this particular notation. So we have to give both the indices for the 2 dimensions, and in the first dimension, the value of the index again should range from 0 to the size of that dimension, and this is true for all dimensions. So the value of j in this example, assuming the previous declaration where the number of rows was m and the number of columns was n, the value of I should be between 0 and m minus 1, and the value of j must be between 0 and n minus 1. So the indices range from 0 to n minus 1, where n is the size of that particular dimension. So here are some examples of usage of array elements. Aij assigned 5. So again, an expression denoting an array element can occur on the left hand side or on the right hand side. So this is initializing the ith jth element of the array A to the value 5, and here the jth ith element of the array A is being assigned to the value of the ith jth element of another 2D array B. Okay, so this is simple enough. Let's now look at an example program using 2-dimensional arrays. So let's take a familiar problem from matrices. So suppose the problem is to read take as input a square matrix from the user of size at most 10 by 10. That is, the matrix that the user gives may be smaller than 10 by 10, but it can't be larger than 10 by 10. And this limit has to be placed because recall that when we declare an array, we have to declare the size of the array. And so if we declare the size of the array to be 10, we cannot store more than 10 elements in that array. So that's why we are saying that the matrix that we read from the user should be of size at most 10 by 10. We are supposed to compute the transpose of the matrix and print the transposed matrix. So let's start developing this program. This is the beginning part. We define a symbolic constant representing the maximum size of any dimension of the array, and here are the variable declarations. N is the actual matrix size that we are going to read from the user. This, remember, may be less than 10 but cannot be more than 10. This A is the two-dimensional array that we are declaring. Note that the size of both dimensions is max size, which happens to be 10. I and j and t will use as temporary variables for looping and other purposes and so on. Okay, so the first part is simple enough. The first, we have to read the matrix from the user, and for doing that, let's first ask the user for the matrix size. We have to ask only the size in one dimension because we are assuming that it's always a square matrix that we are reading. So this should be familiar, this do while loop should be familiar to you from the last lecture, and we are using this to continuously prompt the user for entering the size of the matrix till he gives an appropriate size, and the appropriate size for a matrix will be something which is at least 1 and at most max size. So as long as the value of n is less than 1 or greater than max size, which is 10, we keep giving this prompt to the user to enter the matrix size and reading the value of n. So finally, when we reach here, we have read the matrix size n, and it is known, it is guaranteed to be between 1 and 10. And finally, we have to read a matrix. So for reading a matrix, we have to read each element a, I, j of the matrix. In the usual matrix notation, we write rows, we write the matrix row wise, and so therefore we'll expect the input in the same fashion. And so for doing that, we have used two nested for loops here. The first for loop runs from I is equal to 0 to n minus 1. Note that n is the actual size of the matrix. So the number of rows is n and number of columns is also n, and so the row indices we'll use will be from 0 to n minus 1, and the column indices that we'll use will also be from 0 to n minus 1. And this kind of a nested loop structure is very common for manipulating structures like matrices, because this allows us to individually process each element of the matrix one by one. So this outer loop runs for every row of the matrix, and for every row this inner loop accesses elements in every column of the matrix, and together these loops will ensure that we access and process each element of the matrix one by one in the row order. And for each element of the matrix, right now all we need to do is to read its value. So we use a scanf statement to read the value of the matrix. Okay, let's before writing the program further, let's think a little bit about how we are going to transpose a matrix. So let's assume we have a matrix looking something like this. The transpose of the matrix is the matrix which has the rows and columns interchanged. So the transpose of this matrix will be this matrix. So the question is, how are we going to convert this array into this array? One simple answer could be that we use another array variable of the same size and assign values in the various elements of this array such that the value at a particular element is the value of the element at the mirror image with respect to diagonal of that element in the original array. That is, this value should be placed at this position in the final thing. So that means that if this new array is called B and the original array was called A, then we should set Bij to A Ji. So that's one way of doing this. But suppose we want to do it in a different fashion and we want to transform the original matrix itself so that it becomes the transpose of itself, then we need to do something different. Let me write the matrix again. And let's write the transpose again too. So let's look at these two matrices. If you note, the diagonal remains the same in the transpose, and if you take any element other than the diagonal, then that gets interchanged with the mirror image of that element on the other side of the diagonal. So you had 6 and 8 here, and we have 8 and 6 here. So that means what we need to do is that for all elements on one side of the diagonal, let's say this triangle or this triangle, the lower triangle or the upper triangle, for each element in, let us say, the lower triangle, suppose we swap with the corresponding element in the upper triangle, that is Aij is swapped with Aji. If that happens, let's say for this and this will become 4 and this will become 2, and similarly this will become 3, this will become 7, this will become 8, and this will become 6. So what we need to do for implementing this algorithm is to write a loop which accesses all elements in the lower triangle of the matrix, and for each element in this lower triangle it swaps it with the mirror image of that element in the upper triangle of the matrix. The elements on the diagonal need not be modified at all because they remain at their original positions in the final matrix. And the one final thing that we need to do is to find out how we swap two array elements, and the procedure for that is very simple. Suppose you have to swap two variable values of two variables x and y, then clearly swapping like this will not really work. This will not work because let's say x had the value 5 and y had the value 7. When x is assigned the value y, it becomes 7 and the original value of x is lost. So when we do the assignment y assigned x, the value of y remains 7. Instead of doing this, what we need to do is to take a temporary variable, and before we assign to x the value of y, we have to store the old value of x into the variable t. So this is what it could look like. So when we do this, let's see what happens. When t is assigned x, the value of t becomes 5 in this example, and then x is assigned y, so x becomes 7, but we have not lost the original value of x because it is still available in t, and so the value of y is changed to the value of t, which now becomes 5. And the same procedure can be used for swapping the array elements. So having understood this, let's go on and see how we can write the program for implementing this algorithm. So coming back to the program, having read the matrix, let's now transpose this. So we have this loop here, and you will notice that it is a slightly different loop. The first outer loop is the same as before for I from 0 to n minus 1. So this will run once for every row in the matrix, but for every column in the matrix we want to access only the elements in the lower triangle of the matrix. So the array elements in that row that should be accessed are the ones which lie before the diagonal, and the diagonal element in the row I is at column I. So therefore we should only access array elements at columns 0 to I minus 1, and so therefore you can see that this loop runs from 0 to I minus 1. It terminates when j becomes equal to I. So for each element in the row before the diagonal, we have to swap Aij with Aji. So we use the swapping technique that we just saw. T assigned Aij, Aij assigned Aji, Aji assigned T. So this swaps the ith jth element with the jth ith element, and that's the end of the loop. Note that the inner loop has 3 simple statements in its body, and so therefore they have been clubbed into a compound statement using these curly braces. As far as the outer for loop is concerned, the body consists of this single for statement, and therefore the braces are not required. So finally, when the loop ends, it's time to print the transpose matrix, and we just print the matrix row wise. So for each row we print all the elements one by one. So this loop will print all the elements in the ith row one by one. Note that after the %d there is a blank space, so that after printing 1 there is a blank space left in the output, and then the next array element is printed, and so on. And after this entire loop has finished, so the first row in the transpose matrix has been printed. So let's say that was 1, 2, 3, and then after that we want to start printing the next row on the next line. Note also that there was no \n in the format string of the first printf, so that will ensure that all these three values, or all the n values of the same row, are printed on the same line with a blank in between. But at the end of the row we want to go to the next line, so that the next row is printed on the next line in the familiar matrix notation. Therefore, once this row has been printed using this inner for loop, we print one new line character using the familiar putchar function. And note that now for the outer loop, in the body there are two statements. One is this for statement, and one is this statement calling the library putchar function. And so therefore we have enclosed these statements in braces for the outer loop, and that's the end of the program. Okay, let's now see how two-dimensional arrays can be initialized. That's again very simple. A two-dimensional array is essentially considered to be an array of one-dimensional arrays. That is, if we have an array of size 2 cross 3, it is considered to be an array of two arrays of 3 integers each. And so it can be initialized like that. So we have to give the value of each row, which itself is an array, within the curly braces. So this is row 0 and this is row 1. Within row 0, this is the element at column 0, column 1 and column 2, and so on and so forth. So this is fairly straightforward. Next, let's quickly see how we can use arrays with dimensions higher than 2 or more than 2. And the ideas are very similar to what we have already seen for two-dimensional arrays. The natural generalizations hold. So we can declare and use arrays with any number of dimensions in very similar ways to what we have already seen. For example, a 3D array could be declared like this, giving the sizes on all the 3 dimensions, and when we access an element of the array, we again have to give the indices at all the 3 array dimensions. So this is the end of today's lecture. In the next lecture, we'll be talking about some special kinds of arrays which are known as strings, and which are very useful in manipulating data which are which comprises of text rather than numbers. So we'll look at strings in the next lecture.